Hello, welcome to today's video. Today we're going to be looking at finding the binomial expansion of something of the form a plus bx to the power of n, where n is a negative or fractional index. So let's get going and start by looking at that. So first things first, mention what we've done already. We should already be familiar with finding the binomial expansion of 1 plus x to the power of n, where n is a fraction or a negative power. So that's fine because it's in the formula booklet. We also dealt with what happens if there was a number or a coefficient in front of the x, because all you had to do was effectively the same method for 1 plus x to the power of n, and all we'd have to do is do a substitution, and in our expansion for 1 plus x, replace all the x's with our bx term, and then just have to deal with any dealing with the indices that have to be applied to the b as a result. The issue we have, though, is what happens when we start to have a number other than 1 in front. Because the trouble is, all of a sudden, it's not so clear to see what or where I should be substituting things to deal with this. Because the trouble is, 1 is just a number, and therefore the places it will have an effect on will just appear as numbers within the binomial expansion. But because we're in maths, there's numbers everywhere. So it's impossible to see which are numbers are caused by that 1 and which are numbers which are caused by other parts of the binomial expansion, like the power or the coefficient of x. So therefore, we can't deal with that number, the constant term, by just doing a substitution. We're going to have to do something a little different to deal with that. So here is the method, and we're going to do it to a particular example. So let's have a look at the example 2 plus 6x to the power of a half. Okay, so what we ideally want is, in an ideal world, this would be an easier question because it would have a 1 there rather than a 2. But unfortunately it's not. But we can use that logic to help us. We can try and rewrite this problem in a way that it's in terms of a binary expansion that does have a 1 in it. And so that's what we're going to do. What you've got to do is you first got to try factorizing the constant term out of the algebra inside the brackets that are currently there. So that means we've got to write our big bracket still with the power of a half, and then inside those brackets do that factorization. So I'm going to factor out 2 from that algebra that's inside. So I'm going to write the number 2, then some more brackets, and then I'm going to have what's left after I've effectively divided by 2, which would be just 1 plus 3x. Now, the reason that's going to be helpful is because now we can make use of a certain index law. There's an index law that says if we have this, then the product of two things to a power is the same as those two things individually to a power and then multiplied together. Remember, that wouldn't be true if there was a plus in between them. It's only because they're multiplied that the power works that way. Anyway, what that allows us to do is it allows us to now, despite us having brackets within brackets, it allows us to go back to splitting this up into two separate things that are individually a lot nicer to deal with. It allows us to rewrite it as 2 to the power of a half times by 1 plus 3x to the power of a half. And this is useful because it now means that my original question is just root 2, or 2 to the power of a half, lots of whatever the binomial expansion of 1 plus 3x to the power of a half is, which is something we're happy about because now the binomial expansion part of the problem is now just a binomial expansion with a number 1 as its constant term, which is good because it then allows us to use the same method that we were using before. So therefore, continuing this problem on, that means we're going to end up with finding 2, or root 2 we should say, to the power of a half. Let's rewrite it as that. Root 2, lots of this expansion, and to do that we use the formula. So that would be 1 plus n, which is a half, lots of our x term, which is 3x, and then we're going to just follow the formula on from there. Half times by half minus 1, all over 1 times by 2, all times by 3x all squared. And continue that on, 1/2, lots of a half, minus 1 times by half, minus 2, all over 1 times 2 times 3, and that's going to be multiplied by 3x to the power 3, and so on. Depends on how many terms you want. And then it's just a case of then just simplifying it all. So I'm going to write the root 2 there. I'm going to simplify all this. That's going to be 1 plus 3 over 2x. I'll deal with that in a, well, 3x all squared is going to be a 9x squared. But then I've got to multiply that by this coefficient here, so I'll do that separately. That's minus 1/8. And then we have plus 16th, 1/16 for the coefficient there, but then inside the 3x cubed becomes a 27x cubed. And therefore then we can finally multiply all the brackets and simplify. It means we're going to be left with, at the end, just root 2 plus 3 root 2 over 2, lots of x, minus 9 root 2 over 8, lots of x squared, and then continue this process on, so plus 27 root 2 over 16, lots of x cubed, so on and so forth, depending on how many terms they want. So that's how you deal with it. Just one more quickly. I won't go through the entire question this time. I'll just show you how you started off. So let's say we've got, 5 minus 9x this time to the power of minus 3. Okay, so step 1, we're going to factorize what's inside the brackets already. So we're still going to have the big brackets with the power of 3, but then we're going to write 5, and then inside that will leave us 1 minus 9 over 5x. We then use index laws to split that up, and we can therefore rewrite it as 5 to the power of minus 3 times by 1 minus 9/5 x to the power of minus 3. And therefore that means if I want to find this expansion, all I've got to do is 5 to the power of minus 3, which is 1/125th, in other words 1 over 125, lots of the expansion of 1 over minus 9/5 x, all to the power of minus 3, which can then be approached beyond there using the same method. Okay, that's all there really is to it. Hopefully that was useful, and I'm sure I'll see you again soon.